Hey guys, Anthony Whitlock back again, second video. So I put a post out on social media basically asking what people wanted to learn about or have clarified a little bit better than they understand it as it is. The biggest thing I got was grid to ground. Those grid to ground conversions from state plane coordinates, extending the distances to match real time on the ground distances. To understand that and to explain that, you guys have to understand a lot of other things as it relates to GPS. So this whole thing is going to involve, first of all, ellipsoids. Second of all, datums, understanding realizations of datums. And then eventually we'll get to the state plane coordinates and what you're dealing with converting those distances and still working in the state plane system, but bringing it up to the ground so you can actually be on a site and measure a published value and hit it on the ground. All right, so let's dive in here. It's 11 o'clock, so I'm drinking coffee. Hopefully it's enough. All right, ellipsoids. What you have to understand, or it's important you understand, I think anyway. GPS works in Earth-centered, Earth-fixed coordinates. So what you're seeing normally with a latitude and longitude, or northing and easting, is totally converted by your collector, by our software, in split seconds. So what's really being received is an Earth-centered, Earth-fixed coordinate value. It's taking that based upon your position and our collector settings with whatever ellipsoid we're using, whatever local datum we're using. That Earth-centered, Earth-fixed is then converted to a latitude and longitude, a position on the ellipsoid we're using. So you're getting a latitude and longitude. From there, with your published local system that you have in your settings, that latitude and longitude is saying, okay, I'm here on the ellipsoid. That means I'm here on the surface of the Earth. It's all huge mathematical calculations that's being done for us, so no one really understands it unless they really research this stuff. So when you're dealing with the ellipsoid, you're dealing with a mathematical calculated ellipsoidal shape of the Earth, which is calculated from what we know to be the center of the Earth now. It's basically kind of accepted. It's 20,906,000 feet to the center of the Earth from this ellipsoidal calculation. It's the radius of the Earth. So now that you know that, now that we have this ellipsoidal thing, you understand that has nothing to do with the surface of the Earth. It is strictly a mathematical calculation to give us the best fit spheroid that the Earth is, with flattening at the top, flattening at the bottom, and then the rest is going to be kind of more spherical. Basically what that is it's a reference system. It is really just a reference system so that we can make our mathematical calculations and how GPS all comes together and works. What that is, or what that's doing, is that gives us our latitudes, our longitudes, and a reference system to position the Earth, everything on it, all these positions. Every time you take a shot, you're getting a latitude and longitude. That's based upon that ellipsoid. To go with ellipsoids, which I know that I'm giving rough explanations, it's just that this is going to add up to a ton of stuff, and it can get really confusing really quickly. I'm trying to make it as simple as possible. So we're using GRS80 or WGS84. They're almost exactly the same. The difference is there's about a 2-meter difference from center of Earth positions. So your coordinate values would be different if you tried to compare the two. Other than that, they are mathematically identical. North American datum of 1983. I'm just going to stick with that. There's North American datum 1927, which is based upon the Clark ellipsoid of 1866. Not going to dive in there. It's all important. It's a whole history of things. You really will understand GPS better if you do your own research and check that stuff out. But for this video, I'll be here for 2 hours trying to explain all this stuff. So, NAD 83, 1986. Let me touch base on parentheses that get attached to datum names. Extremely important. People ignore them. People will publish a control sheet or a survey and say just totally whatever is based upon NAD 83. That's all they show. That's not even real. NAD 83 without parentheses with 1986, just NAD 83, that's not a real datum. That doesn't exist. It never has. NAD 83 1986 is the original North American datum of 1983. It's the one that superseded NAD 27, NAD 27. So, now that we know that, pay attention to the parentheses. I'll have to dive in there to explain the realization part of datums as well. So that's coming up. What you need to know is that is a local system. When you are in the North American datum of 1983, it is a localized system placed upon the ellipsoid, or at least based upon the ellipsoid. So what you're getting is a best fit, actual true positions upon the Earth, best fit to fit North America. So what's happening from there, you're getting your position upon the ellipsoid, you're mathematically calculating, because these are all published datums, that's the stuff in your software that's saying you're at this latitude and longitude, that equals this northern and easting upon NAD 83, 1986. So, NAD 83, 1986, there's been a bunch of realizations that supersede it, or I won't say supersede because it's still a perfectly good datum, you can still use it. It's just not as accurate as the following. So NGS has core stations. They've had it for a really long time now, continuously operating base stations, always collecting data from satellites. The data they're collecting is utilized from now till the end of time. It's just constantly being collected, allows the government to reanalyze things. What it's doing is NAD 83, 1986, you have X amount of base stations, X amount of data on the actual surface of the Earth. Over time, all that data is collected, reflected upon, researched, analyzed. Boom, they find out that position on the Earth is not where we thought it was. You're getting more accurate measurements and a lot more of it. You realize, okay, in relation to the center of the Earth, that position is actually over here. And that's how you get a new realization. They do it nationwide. They get enough information where they say, okay, it's time to change it, time to upgrade. So there's a ton of them. Well, I'll just go with like NAD 2007 or NAD 83 parentheses 2007. We're on 2011 right now. That's actually about to be updated and changed. Their government's going to change everything coming up here shortly. I haven't researched it enough to explain it. That'll probably be another video. I really should dive into it. However, we're on 2011. Never ignore the parentheses. That's the most important thing you can do, because if you say you're in NAD 83, 1986, and you're actually in NAD 83, 2011, you're going to have a difference in your coordinate values. You will be wrong. It will not work. From there, I'm trying to kind of rush through this because it's a lot. You've got your local datum, which is going to be based upon northing and eastings, right? All those northings and eastings are being converted from the latitude and longitudes. All the latitude and longitudes are being converted from Earth center, Earth fixed coordinates. You'll never see Earth center, Earth fixed, but I want you to know that stuff's actually happening behind the scenes. Let's see. Datums and realizations. Hopefully that explains realizations a little bit. It's corrections of, hey, we thought everything was here. Turns out it's actually over here. Let's adjust things and correct things. So I'm going to talk about site calibrations as well. I think that's really important, and I think there's a lot of surveyors out there who don't fully understand what they're doing, and that's a big problem. If you're messing with calibrations and you don't understand them like in full, that's a dangerous game to play, especially with construction and things like that. So we'll get there. State plane coordinates. I'm not going to go into map projections or any of that stuff. I've got a picture here. I'm going to attempt to try to explain this a little bit. All right, guys, so this is what we got. You've got the surface of the Earth, the ellipsoid right there. This rounded thing is the ellipsoid. And you've got the geoid. You've got the state plane grid. This is the grid. This is what your grid coordinates are going to be based in. This is what your ground coordinates are going to be based in. You've got the center of the Earth. The accepted average distance of the center of the Earth is 20,906,000 feet. So first of all, let me just get the scale factor. So there's two scale factors here. You've got the elevation scale factor, then you've got another scale factor from grid to ellipsoid. It's just called the scale factor. So elevation scale factor, scale factor. So you're going from the ground to the ellipsoid to the grid. As you can see, because you're coming from the center of the Earth, as you go higher towards the ground, your distance is going to become greater. This is going to be your shortest distance on the grid, middle, longest. So the reason this is done is because what you're trying to do, this is for kind of larger projects, really big projects, to take the curvature of the Earth out of your coordinate system and just remove it. And that way, you don't have to deal with the curvature, and everything you measure is going to be relative to each other. There's not going to be much distortion. There's always going to be distortion, but this will relieve a ton of it so that you can work on that state plane grid. So we scale to ground also for boundary stuff. We want to be, you're not going to do a boundary survey in grid distances. That is the last thing you want to do, in my opinion. Even if you state it, I still don't think it's right. So basically, you're going to want to scale from the grid, which is going to give you a distance. This is going to be the points on the grid. This is going to be your points on the ellipsoid. And these are your points on the ground. To get from grid to ground, you're going to have to do the inverse of your calculated combined scale factor. You come up with your combined scale factor by going from ground to ellipsoid to grid. So you have to take the inverse of that. To get to here, it's going to be less than 1. To get to here, it's going to be less than that. So the way you calculate your elevation factor, we've got 0.1 and 0.2, right? This is your ellipsoid height. H1 is for this point here. H2 is the ellipsoid height of this point here. You need to average that, basically. Is the best way to do it, because if you have a lot of vertical relief, it will affect the scale factor in the calculations. If you hold the biggest one here, you're not going to have distances in between these two for the site that are really, you're going to have more distortion in your distances. So what you want to do, you're going to average your ellipsoid height here, add it with this ellipsoid height here, divide by 2, you've got your average ellipsoid height for your project. What you do then is you've got your 20,906,000, right? You're going to do 20,906,000 over 20,906,000 plus H3, which is your average ellipsoid height. What that's really going to do, let's say your average is a 5280. I'm in Colorado, so I'm used to the big numbers. Your average ellipsoid height, we'll call it 1 mile, 5280. So that's going to be 20,906 plus 5280. Divide that by that, and you're going to come up with a number. I'm not going to do the math right now, but basically you're going to have less than 1. It's going to be like 99995 0.52 or, random. Don't worry about the actual math. Basically what I'm telling you is you're going to be less than 1. You're coming from up here with a longer distance, coming down here to a shorter distance. That is your elevation scale factor, the number you calculate from here from your averaged ellipsoid height of the project. The scale factor, the reason you can't find any information out there on what the hell this thing is and how to calculate it is it's really complicated. I'm not even going to go into it. It's more so these things are published. Years ago, they had tables where if you were at this latitude, you would be this. It would know roughly where your ellipsoid height was and where that ellipsoid was in relation to the grid. So they used to have just charts where you'd say, okay, I'm here. This is approximately what it is, and this is why it's kind of just published information now. It knows where your grid is. It knows where your ellipsoid is. It knows where you say you are on the ellipsoid. It's automatically calculating this. What it's doing basically in rough form, it's taking your grid distance and it's dividing it by your ellipsoid distance, your geodetic distance between these 2 points. And then you're coming up with that number, which is going to be less than 1. And that's the scale factor. You're going to multiply your elevation factor by your scale factor, and that's going to give you the factor for these coordinates, bringing them up to ground, an actual physical point on the Earth. So what you need to do or take into account, I guess, is really just how this works and what's happening. The reason your distances are getting greater is because you're multiplying by the reciprocal or the inverse of your combined scale factor. Combined scale factor is going to be 0.99965. It's going to bring you down here. To get back up, it's going to be the inverse. 1.0035. Boom, your coordinates are changing by that, and you get up here. The distances don't change by much depending upon how big your project is. If you have 2 miles between these points, you're going to see a difference, that's for sure. If you have like a 1,000-foot by 1,000-foot site, you're going to see a few hundredths between the two, maybe. But the whole point of this is to just kind of get your head around the concept here. Going up from the center of the Earth, which everything is kind of based upon here, distances get longer, distances get shorter as you come to the ellipsoid. Distances are as short as they're going to be in our state plane grid system. What's important is you understand the concept here. So you're coming from now the grid with your grid distance when you're measuring in state plane. You're going to take your combined scale factor, which our equipment is going to give us for us. This is not your combined factor. This is your elevation factor. You have to multiply this by the scale factor to get your combined scale factor. That's going to be even smaller than this number. It's going to be more like 0.99965, something like that. So with that, once you have your combined scale factor, you're going to divide it by 1. So 1 divided by your combined scale factor is going to give you the scale factor you need. It's going to be 1.00035 to get from your grid to your ground. Another thing I want to touch base on with your grid to ground scaling, it gets overlooked constantly. I see control sheets all the time that do this. You have to publish the position you're scaling from. It always gets looked over. It's extremely important. So in Colorado, fortunately, well, kind of fortunately anyway, it is a CDOT standard to scale from 0, 0. And what that means is the origin of your state plane system, your zone. In Colorado, I'm mostly in central zone, but there is a north and a south. They have you scale from 0, and that's so that it can kind of always be retraced. It's basically publishing the value without publishing it. It's just their standard for if you do a CDOT project here. Scaling from 0, 0. You're using your project height, your average project height of where your project sits, and you're using that calculated combined scale factor for the local right there where you belong. That's the combined scale factor you're using. You're just keying it in instead of having it calculated from the scaled position. So if you calculate from 0, 0, and you do calculated scale factor in your collector, calculated combined scale factor in your collector, it's going to give you a scale factor from the 0, 0 location down to the grid. You don't want that. That's a problem. You'll never do that. You want your local scale factor. So you're going to calculate it yourself for your local latitude and longitude, your local project site. It's going to give you your combined scale factor up to ground. You're going to copy that, save it, whatever, write it down. Then you're going to say I'm scaling from 0, 0, northing and easting 0, 0 for the origin of the state plane system, and you're going to key in that scale factor. That's going to, what that does, and the reason it's so important to publish where you're scaling from, that will put you 1,000 feet away in a coordinate system anyway, coordinate values. Your project's going to sit 1,000 feet away from where it would if you just used your local scaling position. A lot of people, and that's drastic because you're coming from 0, 0, 1,000 feet. It's crazy. Taken into account, but that's a good eye opener. If you have a shift in your project somewhere and you're like, what the heck's going on? If you're 1,000 feet from where you think you should be, boom, 0, 0. Try scaling from there. All of a sudden, everything matches up where it should. You're good to go. That's why CDOT does it, I think. Another thing, it doesn't matter if you're scaling from 0, 0 or your local project site. That's just a good eye opener. Everything should be the same. The problem I see most is when there's a local system. You've got a local project right here. I don't care if it's a construction project and people are scaling from grid to ground. They say they're scaling from grid to ground. They tell you the scale factor. Everything you need is there except for the latitude and longitude they've scaled from. Whether it's a point at the bottom of the site, whether it's a point in the middle of the site, I don't care. You need to tell people where you're scaling from. That will shift your coordinate values depending upon what point on the site they've scaled from. It gets overlooked all the time, like I said. Just be aware. If you're going to publish a control statement stating modified state plane system, scaled from grid to ground, this is the combined scale factor, just add in there, scaled from either CP whatever, scaled from latitude and longitude whatever, I don't care. Tell us. It's important. We can't get on your system exactly without having that point. All right, so moving on back to site calibrations. And if you guys have questions, feel free, message me or post a comment or whatever. I'm doing this to help the surveying community. If every surveyor out there has a better understanding of what we're dealing with on a daily basis, then that's a much better thing than if you don't, that's for sure. Profession as a whole, we need to educate ourselves. We need to keep up with technology, standards, all that stuff. So what I want to talk about next is site calibrations. And like I said before, I think they're extremely important. I think everyone who's using them needs to understand what they are. To put it simply, it is just, I'm going in the field. These are my published coordinates. For someone did a topography survey. Engineers designed on it. It's now going to construction. You've been hired to do the construction staking. You have existing control in the ground, which control the design. It's what the design is based upon in that coordinate system, right? A lot of times it's a random system. It can be a 10,000, 5,000 system, northings and eastings. There's no published datum to get on that. So you have to do a site calibration or run total station just with those published values. If you're using GPS, I want you to understand the site calibration. So I'm going to draw you a picture. There's multiple ways to do this. A lot of guys will tell you, you have to have it this way. You have to have a box or more points around your site surrounding it. I don't like that theory because I've been on a lot of projects where things off-site have to be staked out. To me, if you leave that little boxed area or large boxed area, whatever, as soon as you go outside of that, you're going to have distortion in your projection. You're encompassed to this site, all of a sudden you leave that site by whatever, you're going to start to have distortion. You're no longer controlled by the exterior boundary of your site. So I'm going to draw a picture here and try to explain it. This is your construction site. you've got to get on their existing control, which is all these boundary corners, let's say. That's a lot more control than you'll typically get on a construction project, but it's better to have more, so let's go with this drawing. So a lot of guys will say you need to occupy each one of these points, right? Let's say they're all based on a 10,000 system, 10,000 5,000 system, whatever. Some people will want you occupy each one of these, calibrate to every one of them. So a calibration is basically saying my shot here, point number 1000, my shot, it's control point 1. You're saying the published values you get for control point 1, 10,000, 10,000, your shot in a no projection, no datum situation. This is all related to Trimble. It's likely very, very similar or the same in any other system. So you've got your point 1000 is your shot, published values of point 1, CP1, 10,000, 5,000. You're in a no projection, no datum. That is extremely important you understand that. If you're in a state plane system or something like that, and then you add a site calibration, it's likely you'll end up with some error around the site. You're mixing and matching things that you shouldn't be, in my opinion. You should be on a no projection, no datum. It should simply be, I don't know where I am on the Earth. This northing and easting equals the latitude and longitude I got. When you're in no projection, no datum, all you're going to get is latitude and longitudes. You're not going to have any northings and eastings. You're not going to have a clue what system you're on. There's nothing to give you northings and eastings. That's what you want. You want your shot, your latitude and longitude, to equal this coordinate value, this northing and easting. Then you come over here, this northing and easting, same thing. Next shot, you want it to equal that. You're going to go around the site. A lot of people prefer this, and I understand why. If you can stay within your site, that's your best calibration. I am used to often having to go off-site, so I don't like using them this way, but it's perfectly fine to do it. So in this particular instance, you've got your entire construction site. You're calibrated to all these control points here. Boom. You've got to stake this off-site sanitary manhole and line, which is 1,200 feet long, away from your calibrated site. That introduces too much distortion for me. I think for a manhole, a sanitary manhole, you'll get away with it. I don't think anyone's going to have an issue. You're not going to end up 40 feet from where you're supposed to be or anything like that. I prefer not to do it, being limited to the site and then going 1,200 feet away. I prefer this. I basically I tie every single point. Those are my check shots. I take the best line I can make out of my existing control that's going to split the site in half and give me the bandwidth or length that I need to get out here without having a lot of distortion. So what I personally would do, I'm going to get into vertical later, but so for horizontal calibrations, what we're dealing with, trying to get on the site, I'm doing this. I come off this control point here, this equals this northing and easting equals however I shot it to be with my longitude, latitude. I come down, I make this line cutting the site in half as best you can. Boom, I calibrate to this too. As long as these published values are good values and you don't have any issues with them, this line is going to control my entire calibration. As soon as I do this, I immediately go and tie every other control point and verify that I don't have error, not enough to make it an issue. If you miss it by 300ths, you're going to do that anyway. If this was all set with GPS, that error is already incorporated into your control, so it doesn't matter. You need to be close enough and firm enough that you can stake this entire construction site with confidence. If you miss these things by half a foot, you've got an issue. There's something wrong with the published values. You have to go no projection, no datum, site calibrate to these 2 points. Everything should check. All these published values should check, right? Let's say this manhole is existing. You're tying in the site to the existing. Somebody surveyed that along the way. They had to have it surveyed to design it. Take a check shot. Confirm that coordinate value is what they say it is, and that you don't have error in it. At least a significant error that concerns you. Anything over half a foot or more, big problem. I look at 3/10 as a big problem. If you can hit it for a tenth, you're solid. That's plenty good. If you hit it for 2/10, you're still solid, still a concern though. Why am I missing it by this much? I'm hitting all my control better than that. You shouldn't miss it by 2/10, in my opinion. But now I look at this almost as a basis of bearing, controlling the orientation of the sight, controlling the entire sight, left or right of the line. You're not going to have any distortion. You shouldn't have any, or at least enough to be concerned about, going to anywhere on this site, or even going out here to this sanitary manhole and staking this whole line. That's how I do site calibrations. A lot of people will disagree with me. I do it all the time. I've never had a problem. So, I understand their thinking and their concept of what are you doing? You got a box in your site. I've never had an issue. This is how I do it. I don't see a problem with it. Like I said, never had a concern. So, if I did have a concern, I would never teach somebody this method. If there was issues on sites when I do this, I would never explain it to anyone else and recommend you guys can do this. So now that you've got your site calibrated, you're extremely worried about vertical, of course. It's a construction project. We need to have good vertical. Another situation. People calibrate to every exterior point vertically as well. I do not like to do that. If you are going to do that, use every single point. I've seen guys make a fatal mistake of calibrating vertically to 2 points. Even if I was doing this, I'm holding one of these for vertical. I will never use 2 for vertical. You're doing it on an inclined plane. You stray from this, if these 2 are calibrated too vertically, you come off this line somewhere, your vertical is going to shift drastically. You're going to have problems. Okay, so with the vertical calibration stuff, what we're looking for, number 1, select geoid/inclined plane. That's the selection in Trimble anyway. Like I said, I don't know about Leica or other technology or equipment, but that's what you're going to want. Geoid/inclined plane. Now, as far as that goes, I use 1 point, like I said. I'll calibrate to this guy vertically. Boom, I've checked every other one. Vertical hits good. The reason I do that is you don't know how the control was established. Yes, it all has published elevations. However, if it was all established with GPS to begin with, you're going to have vertical error in every single point, and they could go opposite ways. If you're 500ths lower here than you should be, and you're 500ths higher over here than you should be, you've immediately calibrated with a 1/10 of error in your site, plus every other point that probably has error introduced to it as well. That's why I do 1. If it's a small site, I've had a conversation with Dave Doyle. He's retired now, but he was the chief geodetic surveyor for NGS. I met him at a seminar. We had a discussion, and I always had this theory that the geoid basically became irrelevant. If you're on a small local site, you're spirit leveling at that point. You're saying this is this, every other point's going to be relative to it. The geoid's not going to change drastically, most likely, for a small site. This point isn't going to be, the geoid's not going to affect the difference. You're spirit leveling, calibrate to 1, go check the rest, you'll hit them, boom, your site's good to go. Everything's going to be based upon this. Your measurements are just going to be higher or lower than this point. You're good. You'll match everything. So I do 1. Other people don't. They do the whole site, and to me, that's just incorporating error on a construction project. For me, I want to have 1 solid point that I know. I want to hit everything else for about 300ths or less, if possible. And then everything you stake is going to be relative to your control now, your calibration. Everything's going to work. You shouldn't have any issues. The main thing with this and all surveying, you got to make your check shots. You've got to verify what you think you're on is what you're on, and everything relative to it is going to fit and be good. All right, guys, I think that's about it. I think we're a little over 30 minutes of just me talking and explaining stuff. I promise you it was a lot longer than that with all the editing and just verifying information before I explain it. I hope that helps. I did my best to try to make it as simple as possible. If you guys have questions, like I said, comment on it, send me a message on social media or whatever. Just reach out to me. I'll do my best to clarify it if you have questions. That is all I got. I hope this helps, and I hope you guys appreciate it. It takes a long time to do this, and I have 2 kids and a wife, so it's not easy to find time or privacy to sit down and get this done. All right. Well, thanks a lot for watching. I hope it helps.